Okay, thank you very much for joining. It's wonderful to see such a crowd today for our webinar. So our goal today is to tell you about the opportunities for the PRIMA Volume 2 Geo book. And so we're going to do this in sort of two parts. The first part is going to be a set of talks giving an overview of PRIMA, the science, the instrumentation, and then the Geo book Volume 2 itself and some information on how to submit cases, as well as a demonstration of the new exposure time calculator. And then we're going to have time at the end. We will have time after each talk for questions, but we will also have time at the end for smaller rooms to have more dedicated questions on topics that include the exposure time calculator, doing science, particularly with the PI data, so general investigator science, and then just general questions about submitting cases for the Geo book. My name is Elisabeth Mills, or Betsy, so I'm one of the PRIMA co-Is. And so I will be talking today about the PRIMA science case. So I'm giving this talk on behalf of Jason Glenn, the PI, and the other co-Is on the team. So please do excuse me. It is 1 a.m. here, and this is my first time running through these slides. There will also be I also want to note that Mark has kindly agreed to give talks on FIRUS, but he is not the FIRUS expert. So both this session and the next session later today will be recorded. And so I will be taking any questions that I cannot answer or Mark cannot answer, passing them on to the second session and making sure that we do get answers for you. So again, thank you for your patience going through this. But I'm very excited to talk to you today about PRIMA and the opportunities for it. And I'm going to start with the science case. So PRIMA, again, is led by the PI Jason Glenn at NASA Goddard, but it is a joint effort as well with NASA JPL. And so you see that our deputy PI, our project scientist, and deputy project scientist are all also members of NASA JPL. In addition, we have Alex Pope and Tiffany Kataria as our science lead and deputy science lead. So I'm here to tell you about the science, but of course none of this is possible without the observatory itself and the instrumentation complement. So PRIMA is a 1.8 meter aluminum mirror. And one of the big advances here is that this aluminum mirror is actively cooled to 4.5 degrees Kelvin. So this, in conjunction with our suite of instrumentation, as we'll talk about, is going to give us a very large leap in capabilities over prior observatories. Another thing that's a great advance over prior observatories that we're very excited about is a large amount of time for such a probe class mission that will be available to the community, to guest observers. So 25% of the time is dedicated to PI science, but 75% of the time is going to be dedicated. Here, let's see. Is this help? Can the bottom of the slide be seen now? Okay, yes, thank you. So 75% of the time is available for guest observers. As well, it should be noted that the PI time, while this is dedicated to predetermined science, these data will all be available quickly for guest investigators. So PRIMA's instrument complement, which you're going to hear more about in later talks, is two parts. So one of these is an imager and polarimeter. So PRIMager is designed to have hyperspectral imaging. So that means imaging in narrow bands, right? A large number of narrow bands that allows you to quickly build up SEDs of your sources, as well as at the longer wavelengths, it has very sensitive polarimetric capabilities. And so this is combined with spectrometer capabilities from FIRUS. So over the same wavelength range, FIRUS will be giving you spectroscopy up to a high resolution mode that does vary with wavelength. So while we give you a characteristic sort of performance at 112 microns, note this is up to R of 20,000 at the short wavelengths, so much better than JWST in the overlap region. All of this is also enabled by the detector technology. So we're using KIDS or kinetic inductance arrays. And so these are extremely sensitive, again, operating for both of the instruments and allowing us to reach really unprecedented sensitivities and unprecedented mapping speeds. So PRIMA will be in an Earth-Sun L2 orbit, and this is sort of an optimal thermal position, thermal environment for it. The anticipated launch, should PRIMA be selected, and selection between the remaining two mission concepts is anticipated to occur in spring or summer 2026. The anticipated launch would be in 2032. So speaking of the kids and what are we able to do compared to prior observatories? So PRIMA is a great leap in sensitivity that's available. Like, this is the time to do this, right? Because the technology has matured to the point that we're able to get extreme gains compared to prior observatories. So when you compare to Sophia, for example, which did not have an actively cooled mirror, or Herschel, you're seeing gains of many orders of magnitude. This is a map that's showing you mapping speed. So the time to survey 100 square arc minutes, right, to a uniform 5 sigma depth of 3 × 10⁻¹9 watts per meter squared. And so here you really see the power that PRIMA is offering, right? This large gains in mapping speed because of these sensitivities they're enabled. The other thing that this plot doesn't make clear, but that is another exciting advance of PRIMA, of course, is that much of this you can do at the same time. So with Primager, you will be observing the hyperspectral bands and the polarimetric imaging simultaneously. With FIRIS as well, you will be able to observe 2 out of 4 bands simultaneously. So this is large sort of spectral space that you are able to map very quickly. And the sensitivities that we're getting with the kids, the really exciting thing is when you couple this now with an actively cooled mirror, what you are able to get, right, is sensitivities that are no longer limited by the detectors, but are now limited by our astrophysical backgrounds. So limited essentially by the zodiacal light. So of course, in this talk, we're most interested in the science. So what is the science that we can do with these great leaps in capabilities? So our PI science is organized around 3 main themes. And the themes of this are very much related to what can we see in the obscured universe, right? So things that we can both see that may be blocked by dust at shorter wavelengths, but also things where the tracers that we are looking at, the specific lines that we are looking at, are optimally placed at far infrared wavelengths. And so the science that we can best do at far infrared wavelengths includes studying the origins of planetary systems and how planets get their atmospheres, as well as in the more distant universe, understanding how black holes and galaxies co-evolved, as well as with some of the same tracers and the same survey data, how the dust and metals build up in galaxies. And so I'll talk a little bit more about each of these cases. But I want to note at this point, these 3 cases are going to be done primarily through surveys. So surveying sort of anywhere from 200 protoplanetary disks to tens of thousands of galaxies with Primager imaging, and several hundred with spectroscopic imaging with FIRIS. And these PI surveys will again be publicly available. One of our main goals with the PI science, of course, is to guarantee that high priority science will be done for the community, but also to make this data available to the community and to do a broad enough range of science that we're defining a range of mission requirements and capabilities that then will enable a really robust general observer program. So starting with the first case here in planet growth in disk, the goal is to be able to answer questions that are key to our understanding these days of exoplanets, and also just generally the assembly of stellar and planetary systems. So one of the big open questions in exoplanets is understanding how exoplanets migrate and how planetary abundances are tied to the abundances that you measure in the stars. And so PRIMA has leverage here by being able to make very accurate measurements of the overall masses of disks. And this lets you tie your absolute abundances of C and O that you get, for example, with facilities like ALMA, to an absolute measurement of the gas mass. And this is very important because a lot of the tracers that we use, like CO, suffer quite a bit due to freeze out, the CO freezing onto the dust grain, onto these pebbles and structures that are beginning to form in the midplane of the disk. And so PRIMA will uniquely use HD, which will let us get an unbiased measurement and an accurate measurement of the disk mass. In addition, we are very interested, even though we don't see them directly, we are very interested in these pebbles. And one of the questions that is open right now in disks is whether the buildup and migration of the icy pebbles is something that helps drive overall planetesimal accretion. And so one of the things that PRIMA will do will be measuring the distribution of water vapor in disks, the warm and especially the cool water vapor that's inaccessible with JWST. And this then will let us map this to models of the pebble migration and help us constrain these models and better understand how the accretion process is happening inside of disks. In addition, we have some unique solid state features, for example, water, ice, and silicates that are also directly accessible in the PRIMA wavelengths. So moving on to more distant sources and studies of galaxy evolution. So big questions we have here, of course, are we see in the present day universe very tight correlations between galaxy masses, masses of the host galaxies and the masses of the central supermassive black holes. And a big question we have is understanding how that came to be, right? So what are actually the processes that drive the growth, and how do these structures, the very large scale galaxies and the very small scale supermassive black holes, how do they talk to each other? How do they co-evolve? And so PRIMA's unique handle on this is that we have the ability to simultaneously, so in the same sample of galaxies, measure the black hole accretion rate as well as the dust-obscured star formation rate. And so by measuring these at the same time over sort of a large range of cosmic time, so since cosmic noon to the present day, our goal is to be able to robustly distinguish between models for galaxy growth. So being able to actually make very specific constraints on testable predictions from models that tell us that may predict, for example, whether black holes are growing slowly compared to galaxies or growing quickly compared to galaxies, and actually be able to rule models out. With this sample, we will also be able to test other predictions of these models. For example, very fast black hole growth should lead to very large and robust outflows that should be detectable in a large fraction of the galaxies we observe. So we will also be measuring the outflow rates, the key measurements of the cool mass again in these outflows that are suggested to carry away sort of the bulk of the mass in these outflow processes. And so being able to measure these as well in a sample of the galaxies that we're able to probe. But again, getting tens of thousands of these in sort of a square degree survey with PRIMAture. So with the same sort of data set, we can also probe interesting questions about the rise of dust and metals. So understanding how tracers of the dust, the small dust grain PAHs, right, are linked to metals and how this relationship has changed since cosmic noon. So in the present day, we see very specific trends. So we see, for example, that when there is low metallicity, you see significantly reduced PAH emission. And so one question is whether this actually holds, and so whether you can be using pH emission as a clear and correlated tracer with metallicity, or whether this relationship changes, the calibration changes at higher redshift. And so PRIMA will be able to measure again simultaneously, uniquely, both the PAH fraction as well as, and that can be measured actually just directly from PRIMAture, and then compare this to gas phase abundances that we can get with FIRIS for key lines of oxygen and nitrogen, right, that are very sensitive to overall abundance. So I want to also point out that there are wonderful synergies with PRIMA and other instruments that are online and will be coming online. And so I'm turning it over to Hanai to talk about several of these.
Thank you, Betsy. Yes, I would like to emphasize PRIMA on its own is really what producing open up the new window first to the universe. But together with other instruments that are currently available or will be available in the near future, together with PRIMA, there will be a lot more science can be done. Especially right now, Japan is trying to get involving PRIMA officially. So I'd like to showing this example from Subaru telescope. As everybody know, Subaru has a very large field view and it's very efficient in surveying, just like Prima. And so there's a perfect synergy there. As you can see at the bottom left, that's a Subaru HSC imaging. And we also have Subaru PFS for spectroscopy. And also we're waiting for Ultimate to be online, which is in near infrared 1 to 2.5 micron. It will cover very nicely together with Prima's wavelength range. especially try for us to understand the unobscure universe and obscure universe. I'm showing one of the excellent example that Kubo-san from Japan has done using long wavelength data together with shorter wavelength data taken with Subaru. So with a stacking, she found in this overdense region that actually have infrared, far infrared excess emission. But back then, it was rely on stacking to find this very red obscure sources in overdense region. But with PRIMA, it will be possible to detect them directly. That's one of the big advantage PRIMA will have together with this large field surveys at shorter wavelengths. And I also want to show is together with I mentioned like Euclid, Roman, Rubin, they you can see in their CD they cover let us cover the stellar emission, and Prima will cover the long wavelength showing us the dust emission directly. And especially I want to point out GLX Plus, which is a space vessel Japan is planning in 2030 that will cover even longer wavelengths between 2 and 8 micron without, and it's not only having imaging, but also have spectroscopy covering 10 to 20 micron without 30K. And it's very high resolution. But if we just look at the imaging, you can see PRIMA can probe for obscure aging and star formation up to Redshift 4 that can also be observed by GLX Plus or Euclid and Roman. So together we'll be able to see both stellar and dust emission. And finally, I want to touch on this GLX Plus a little bit more. Like I mentioned, R is very high in the GLX Plus, and PRIMA also have very high R in spectroscopy. And both will be able to resolve H2O lines, like Betsy showed earlier. And of course, JWST have a similar coverage as in GLX Plus, but because it doesn't have a high enough resolution, this has been hard for JWST to do this. And together with GLX Plus and PRIMA, like I show on the left-hand side, in the protoplanetary disk, GLX Plus can observe the innermost region of the H2O, and PRIMA will looking at the more outer skirt of this protoplanetary disk. So for when you think about PRIMA, I would like to encourage everybody to also think about what kind of synergy PRIMA can generate together with the telescope you have access with. That's all. Thank you.
All right. So again, the key thing for today is really 75% of PRIMA's time being dedicated to general observer science. So the PI science is again here to ensure key science gets done, but also to define mission requirements, right, that make observatory capabilities that let you do the science you're excited about. So we want PRIMA to be your observatory, and one of the ways you can help as a community is by starting early to define the science that you would want to do with PRIMA. So this helps us ensure that we have the modes and abilities that are on hand to be able to do this science. And it demonstrates, of course, the community's need and excitement for this facility. And again, all the PI data will be public after a short initial validation period. And so we are excited for the Geo book volume 2 to contain not just geoscience, but ideas of things that you might do with the GI science data, with the PI science data, that sort of demonstrate the rich potential of these surveys. And so finally, I also want to say we're excited that we are moving forward with our new working groups, which should be launching this week. So if you did sign up for a working group, you should be receiving an email this week to get coordinated on Slack. If you've not signed up, there's still a chance to sign up. And we're finalizing sort of the organization of the working groups and the leads right now. And we are excited to have more folks involved and to have you all involved. So thank you so much. I'll take a few questions and then we will go to Mark to talk about instrumentation. Yes, Yalun.
All right. So you
And
mentioned,
I apologize. I want to note Yalun has agreed to be one of our working group leads for the star formation and ISM group. So we're very happy to have him involved with that.
Thank you. Thank you. Right. So I have a question about the GI science that you mentioned, kind of touched on at the beginning. You said I think your phrasing is like the data will be shortly after the PI science being done, the data will be shortly available for GI science. Can you explain a little bit more about how this mechanism is going to work?
Yeah, so the maximum time that it would take would be 6 months. We certainly hope to be swifter than this. We will be able to, and maybe Mark or Denis could speak a little bit more, but we will be delivering data that are calibrated and ready to use. So this will not, I believe, include, for example, catalogs at this point. The data from the survey that you can then use for science.
Cool.
I think we're losing you sometimes, Betsy.
Yes, I apologize. It looked like I broke up a little bit there.
Yeah, but I think I got a gist of it. Also, I'm curious about how I mean, this is so far away, but I'm curious about, for example, for PI science program, would the community know in advance, like, oh, these are the targets going to be done by the PRIMA team. So similar to the GTO program in JWST, like here's what I'll set up, but obviously the PI team that's their program, they'll take a first crack at that. Is that what the PRIMA team is envision how the thing's going to work?
Yeah, so I believe, I mean, at this point, of course, it's too early. We don't know the target list, but I believe that this is something that will be available. So when a field is chosen, for example, as a blind survey field, right, that will be known. It will almost certainly align with one of the well-known, well-studied Roman deep fields in order to sort of enable getting the redshifts of the sources. I also anticipate that, for example, the list of disk targets would also be made available.
Thank you.
If I can add a word, like we're still trying to define what fields will observe what target specifically. So it will not be very precise right now, but with time, of course, we'll have more information. So right now we'll provide some general information, what type of science we can do and what we want to do.
Yeah, one thing I can add is that we're currently working on the section of the proposal that is the data management plan, and this defines what kind of product we expect to be releasing, be it from the PI or the general observers observations. And this is rather ambitious in the sense that the end product that we intend to release should allow significant science investigation. So it's true, we're not yet sure, for instance, whether we would release catalogs from the deep survey, but I wouldn't write that out.
I think the goal is initially we will, right? Like the products and the codes will be the timeline for that, like that would take a little bit longer than just immediately putting the data in folks' hands.
But definitely calibrated data. So for Virus, it's calibrated spectra. For Primager, it's going to be calibrated total power and polarized maps, and as well as SED cubes probably. The question then is whether, for instance, for spectra, you'll be provided with line lists and intensities and things like that. But this is on our table, and we need to essentially cost it in terms of time and manpower to produce that.